Okay, everyone, welcome back. We now have Yuya telling us about semi-classical analysis of two-index QCD using a Hooft flux.
Yeah, thank you very much for introduction, and thank you very much for invitation to this very interesting conference. So today I'm going to talk about my recent work with Hooft at North Carolina State University based on this first paper. And the motivation is to study, motivation is I want to understand the ground state of property of QCD with two-index scope. So basically this is a Lagrangian, so there is a kinetic term.
Okay, everyone, welcome back. We now have Yuya telling us about semi-classical analysis of two-index QCD.
And yeah, I can rotate away by anomalous scalar transformation, but just for convenience, I keep also the topological theta term of SU and group for four-dimensional gauge theory. And this Lagrangian is almost identical to the usual QCD that describes the strong interaction of our nuclear forces. But the difference is this Dirac-Fermi psi is now belongs to not in the fundamental representation of SU and gauge group, but it depends on some two-index anti-symmetric or two-index symmetric representation. And maybe I will focus on this anti-symmetric case. And the reason why this can be interesting is, so for our SU3, so nuclear theory case, so we are interested in the case column number is 3. But in that case, two-index anti-symmetric representation is identical to the conjugate representation of the fundamental representation. So that means that so when n is 3 case, this is the same with the actual QCD. So in that sense, this two-index anti-symmetric QCD gives a kind of the large n generalization of actual QCD. So this is give a different large n generalization compared with the usual Hooft large n limit. And especially, so in the case of Hooft large n limit, number of gluon degrees of freedom is order n squared, while number of quark degrees of freedom is just order n. So basically, if you take large n limit of that large n Hooft type large n limit, then basically gluon's dynamics are dominated, and we insert massless quark as a probe dynamic, as a probe field. But in this kind of two-index representation, number of quarks are also of the order of n squared. So in that sense, this large n limit is described by both gluon and quark dynamics. So in that sense, this kind of large n, another kind of large n limit can be interesting to study some dynamics of actual QCD. And furthermore, so there is a very interesting conjecture given by Adi Armoni, Misha Sifman, and Veneziano in 2003, which is called orient-fold equivalence conjecture, which states that in the large n limit, this SN QCD with two-index symmetric or anti-symmetric quark is equivalent to n equal 1 super Yang-Mills theory. So in that sense, although this theory is not supersymmetric and it's quite difficult to solve it even in the large n limit, but if this orient-fold equivalence conjecture is true, then you can use a knowledge of super Yang-Mills theory to understand its dynamics. So in that sense, this kind of two-index generalization of the QCD is quite interesting. But the question is then whether this orient-fold equivalence conjecture is actually true or not. Especially, so they give a nice proof for the perturbative orient-fold equivalence, but the question is whether that kind of equivalence holds at a non-perturbative level. So this is an interesting question that I want to ask. Okay.
What does prove the perturbative proof? Is it?
So if you expand the Feynman diagram of both theory in terms of the Hooft coupling, then each coefficient, so in the leading order of n squared term is completely same between these two theories. So in that sense, at any order of the perturbative expansion of the Hooft coupling, leading n contribution are completely identical. So that's what they have shown.
Is that just a trivial calculation that just got two indices or both?
Yes, so basically, yeah, right. But joint quark have this so opposite orientation of two indices, but you have to do some charge conjugation flip to transform the adjoint quark group to the
That's why unbroken C symmetry.
Yeah, right. So exactly. So because of that, unbroken C symmetry is a key feature to prove this orient-fold equivalence. And furthermore, this unbroken symmetry is key also for the non-perturbative oriented fold equivalence. And so basically, so in 2006 work by Midhart and Yaffe, so they proved that so this oriented fold equivalence can be obtained by two different kinds of orbifold projection, starting from n equal 1 SO to n super-Yamil theory. So if you pick up some element of SO2n, and if you take this kind of projection for gauge field and gauge zero, then so you get this. You can get n equal 1 SU n super-Yamil theory out of SO2n Yamil theory. But if you flip the sign of the GRU-ino for the projection, then instead of super-Yamil theory, so we can show that you will obtain SUN QCD with two-index anti-symmetric representation of the Dirac fermion.
Maybe it's SUN, it doesn't make sense that it would be SU2.
Yeah, so sorry, this is a type. Yeah, so this is SUN. So yeah, sorry, I made a mistake.
Sorry, this is some kind of twisting or what?
Right. So this is a kind of twisting, or it's really just a projection of the degree of freedom.
Nobody knows what it is.
Yeah, right. I actually do not know what actually, but what is known is if you perform this operation, you can connect these two theories, and you can say that for certain set of observable in the large n limit, correlation function turns out to be identical. So yeah, but
I mean, these theories are obviously not equivalent. They have a different number of vacua.
Exactly. So
in one vacuum, correlation functions for some observers are probably the same in the planar unit.
yeah, exactly. So here what I have shown is so this oriented fold equivalence between super-Yamils and QCD with two-index quarks can be obtained by successive application of two oriented fold projections. And for equivalence of the oriented fold equivalence statement is if vacuum preserves the certain kind of symmetry used in this projection, especially the charge conjugation symmetry and fermion parity in this case, then statement is so connected correlator of charge even bosonic local observable turns out to be same between these two theories. So this is a statement of the large n orbifold or oriented fold equivalence. And the key assumption is vacuum should preserve charge and fermion parity symmetry. But fermion parity case, so if we assume that so vacuum is Lorentz invariant, fermion parity cannot be spontaneously broken. So we can, as long as we assume that these theories have Lorentz invariant vacuum, then fermion parity is unbroken. So really a key question is whether charge conjugation symmetry is broken or unbroken. So this is a question we want to understand. But so that means that so in order to get a non-perturbative proof of the oriented fold, large n oriented fold equivalence, we have to know about the vacuum structure, especially whether what kind of symmetries are broken or unbroken. And this is quite non-perturbative question, and they are strongly coupled, so it's usually difficult to directly attack these problems. So instead, so I give up to directly attack this problem, but let's try to find some nice semiclassical setup to understand or get some hint on the dynamics of QCD with two-index anti-symmetric fork field. And setup I will consider is, so we put this two-index QCD on this small femtotorus, and I introduce suitable magnetic flux inside it. Then in this setup, what I will show is using some, so in this setup, if this size of T2 is much smaller than strong scale, I can apply some semiclassical computation using center vortices. And using that semiclassical computation, I will show that this theory has n-2 vacua according to the chiral symmetry breaking. And I will also check that charge conjugation is preserved. So if you assume that so this T2 compactified setup is continuously connected to so the compactified limit, this is the assumption of the adiabatic continuity. And if you assume this dynamic, so this part is an assumption, but if you accept this part, then QCD of two-index QCD preserves symmetry, which gives some support for the charge for the large n oriented fold equivalence. So this part is, again, an assumption, but there is a good reason to believe it. So the reason why I can believe this kind of the adiabatic continuity is some success for the analysis of the Yang-Mills theory on this T2 compactified setup. So let me give some brief review about how Yang-Mills theory on this T2, on the similar T2 compactified setup is very close to the expected dynamics of the R4, of the Yang-Mills theory on R4. So before studying QCD, to index QCD, let's just work on Yang-Mills theory on the small femtotorus, introducing to Hooft flux. And instead of giving the definition of the Hooft flux, let me just state the outcome of introducing the magnetic flux. So this is a small torus, and since we have a compactified direction, or two compactified direction, we can consider a wrapping Polyakov loop along y and z directions. So this is basically a world line of the heavy quark along this compactified direction. And since we are working on SU and J theory, so these Py and Pg are basically n by n matrices. And if you introduce the Hooft flux, then this is basically a magnetic flux or characterizing a Aharonov-Bohm phase of these heavy quark field propagating along this compactified direction. So that basically says that so this Polyakov loop along y and z direction does not commute up to this center element. So this non-trivial commutation relation up to this center element is nothing but the Aharonov-Bohm phase or what is called the Hooft flux in the context of the SUN gauge theory. And so if you look at this algebra, then you can notice that so if you assign this Py as a clock matrix and this Pg as a shift matrix, then this commutation relation can be satisfied, which states that so basically vacuum configuration of this after inserting to Hooft flux given by this vacuum expectation value of the Polyakov loop along y and z directions. And basically, and if you take a trace of this and they are zero, so that means that so center symmetry along this compactified direction is unbroken at the classical level. And so this is a vacuum configuration, and we have to study the perturbation theory on top of this vacuum configuration. And to study it, so basically we are studying 2D SUN gauge theory coupled to these Py and Pg. And this Polyakov loop behaves as an adjoint Higgs field for 2D effective theory, basically stating that so with this vacuum expectation value, so SUN gauge group for 2D effective dynamics is Higgsing to its center element Gn, because only elements that commute with this Higgs field is just a center element.
I'm sorry, can I ask you just a basic question? I think
Yeah.
Is the situation that you have put the total flux on the T2?
Oh yeah, inside this T2.
So just a remedial question. I think if when that is the case, then Py and Pz are Toft lines. Is that right? Or
No, Py and Pg are Wilson loops still.
The Wilson loops.
Yeah,
okay,
yeah,
I see,
yeah.
I see.
Right,
Okay.
right. Yeah, thank you for
Sorry.
the question.
Okay, excuse me.
Yeah. And with this Higgs expectation value, SUN is broken to its center element. That means that so if you compactify one of this R2 direction, so let's say compactify direction of this R2 as X direction, then it's another Polyakov P sub X should be proportional to the identity. So this is what this Higgs means. So this means that so although so center symmetry for this small T2 direction are both unbroken, while this center symmetry in this R2 or uncompactified direction is spontaneously broken. So this is the classical nature of this compactified setup. So that means that so for this small compactified setup, we are in a confined phase, but for this R2 direction or uncompactified direction, we are in a deconfined phase. So that seems to be different from what we expect for the Yang-Mills theory. And so that's true, and this is bad for the adiabatic continuity, but you can save the story by considering by taking into account the semiclassical tunneling physics by using center vortices. So let me go to the next step, and let's try to incorporate the center vortex in the semiclassical analysis. And in this T2 compactified setup with introducing the Hooft flux, so there is a configuration called center vortex, which is really just like a vortex in this uncompact R2 direction. And the property is this configuration is a self-dual configuration. Although there is no analytic proof for the existence of the self-dual configuration, Gonzalez Arroyo and his collaborators are showing that that kind of self-dual configuration exists by numerical minimization of the Yamil's action with the twisted boundary condition. And with this center vortex defect, if you compute the topological charge, you get some fractional topological charge plus minus 1 over n. So although the total topological charge of SUN Yamil theory should be belong to integer, but with this twisted boundary condition, topological charge of this self-dual excited configuration can be fractional given by plus minus 1 over n. And this center vortex gives interesting tunneling processes. So let's consider again considering this this compactual R2 direction. So this x direction is compactual but still very large. Then assume that so there is some center vortex defect inside this cylinder. And so this is a center vortex. And so you have n distinct center broken vacua. But if you consider the Polyakov loop along this x direction, and if you move it gradually, and if center vortex is crossed, then phase of this Polyakov loop should be shifted by the element. So this is nothing but the non-trivial property of the center vortex. So that means that if you start from some center broken vacua, and if you apply the imaginary time development of the Yamil's Hamiltonian, then for most of the leading contribution is the no excitation. Absence of so there is no center vortex is a leading contribution. So center broken vacuum just to give the same element. But the next leading contribution is given by the center vortex excitation, and that one gives a tunneling amplitude to the next neighboring vacua k plus 1 or k minus 1. So basically, from this kind of the perspective, we are just working on the quantum mechanics with n distinct minima, and there is a tunneling amplitude among those n vacua. And by minimizing this kind of the Hamiltonian, basically you can obtain the at generic value of theta. So semiclassical ground state by diagonalizing this Hamiltonian is turned out to be unique and gap. So in that sense, you can recover the confining vacua by taking into account this semiclassical center vortex configuration. And if you perform dilute gas approximation, so you can compute the theta dependence of each ground state vacua. And there is this kind of theta dependence, so fractional theta dependence is recovered. And furthermore, there are n branch structure. So if you plot the ground state energy as a function of theta, then you get this kind of behavior. So if you change from theta equals 0 to 2 pi, there is a level crossing behavior at theta equals pi. And this is exactly what is expected for the large n confining Yamil theory in 4 dimensions. So, yeah.
I have an annoying question.
Yeah.
There's an ADHM stroke NARM description
of
these center vortices. Because it's just an instant ontology. It's really the D1, D5 system that's a twist on D5.
Yeah, but I do not think on the case of T2 compactified setup that, even with that technique, analytic solution is not yet constructed.
You have to solve partial differential equations.
In
the ADHM.
I think actually against Gonzalez Arroyo, you actually consider this theta within this papers.
I see.
Yes.
So because there is a compactual direction, so there are several compactual directions. So even if you perform NAM transformation, it's a not trivial equation you have to solve it.
So they were trying
some modular function that sits on this torus.
Yeah, sorry, I'm not so familiar.
That is some kind of definitive theta. Okay. I mean, no analytic. Full analytic solution is not imaginary T4 or T2. Okay, but my understanding that this can be done perfectly.
Okay.
Your topological charge is not properly quantized.
Yeah.
Because you have boundary conditions.
Exactly, right. So you have to take twisted boundary condition, right?
No. I meant it's not a compact manifold, really, right?
So this one is not compact. Yeah, right.
From Vx with k, Vx with k.
Yeah. Right. Yes, that's true. Okay, so and the success of this nice reproduction of the 4D dynamics has an interpretation from the anomaly matching both in 4D and 2D. So in the case of 4D Yamin theory, by this paper by Zoha and his friends, so there is a Hooft anomaly of the Yamin theory between center symmetry and 2-pi periodicity of theta, as Mendel explained in the previous talk. So if you introduce a background to form gauge field for the center symmetry, and if you shift theta by 2-pi, then it almost recovers the original partition function, but contact terms for the center symmetry background gauge field are shifted. And so because of this property of the, or because of this anomaly for the theta periodicity, so if you assume confinement at any value of the theta, then so you necessarily require a multi-branch structure. And there has to be a quantum phase transition at some certain value of the theta. And even with this T2 compactified setup, so this one-form symmetry or center symmetry of 4D is split into center symmetry or one-form symmetry in 2D and two zero-form center symmetries. And if you introduce non-trivial to Hooft flux along this T2 compactified direction, then so this anomaly has a non-trivial dimensional reduction like this form. And especially, so only when you insert a non-trivial to Hooft flux, there is a non-trivial anomaly relating to the one-form 2D one-form symmetry. So because of this feature, so only when you introduce a non-trivial to Hooft flux, confinement of 2D implies a multi-branch structure. So in this case, so Hooft flux plays an important role for the adiabatic continuity between 4D and 2D dynamics. And yeah, so maybe I should skip this slide because of the time restriction. So yeah, so because of the success of the semiclassical analysis of the Yamin theory, so let's extend this kind of idea to the QCD with two index quarks. And for this purpose, so anomaly plays an important role. So let me first identify what the symmetry is and what the anomaly is. So QCD with two index quark have a vector-like symmetry like this. So there is a U1 baryon-like symmetry, and when n is even, there is a G2 one-form symmetry. But this is a subtle difference whether n is even or odd, but it doesn't play much role. So let me just assume that n is odd, and we just have U1 baryon number symmetry. And in addition to that, so there is a non-trivial axial symmetry given by this discrete axial symmetry. And interestingly, so there is a non-trivial mixed anomaly between the vector-like symmetry and this axial symmetry, as in the case of the ABJ anomaly.
N plus 2 is this index symmetric, right?
So sorry, I want to consider anti-symmetric case. Yeah, so sorry, I made a mistake. Yeah, so, and to detect anomaly, so we introduce background gauge field for the vector-like symmetry, which is given by U1 gauge field for this one. But because of this division by center element, so you also have to introduce the GN2 form gauge field to properly gauge this vector-like symmetry. And if you introduce this background gauge field and perform axial symmetry, it's a complicated expression, but the important thing is you get non-trivial anomalous case. And because of that, so if you assume that so system is gapped and vector-like symmetry is unblocked, you have to so 4D dynamics should spontaneously break axial symmetry. And the question is what happens if we perform this T2 compactification with introducing this kind of Hooft flux. And if you introduce this Hooft flux, then so if you perform just a periodic compactification, there is no remnant of the anomaly. But if you introduce this background gauge field, background flux for the compactified T2 direction, then 2D effective theory has a non-trivial anomaly, which is obtained by the dimensional reduction of the 4D anomaly. So in that sense, important thing is only when if you introduce this kind of magnetic flux, 2D and 4D dynamics are constrained by the same anomaly relation. So there is a chance for the adiabatic continuity if we introduce this magnetic flux in this T2 compact Frey sector. So since we constructed
So,
a
quick question.
Yep.
I mean, when you put fundamental matter,
okay,
well, not fundamental,
What?
symmetric and
Yeah.
antisymmetric, and you don't have, you have a Z2. One-form,
right.
what? You just
Where?
have a Z2 one.
so here, properly speaking, I'm introducing minimal to Hooft flux using the factor zeta quotient for the U1 symmetry.
Oh, sorry. So you're putting basically U1.
Yeah, so basically U1 magnetic
Fractionally
flux.
one-form.
Yeah, right,
Okay,
right.
Sorry. Yeah. Misunderstood.
Yeah, and
But there is no anomaly involving that, essentially. Or is there?
so there is an anomaly given by this expression. So yeah, it's complicated, but there is a good anomaly that says that this n minus 2 must be broken to fermion parity. So there has to be n minus 2 back.
For a fundamental, there is nothing.
For fundamental, there is
But
no
for
axial
this-
symmetry and no anomaly at all. Yeah, exactly. Yep. Okay. And since we introduced not trivial to Hooft flux for the gauge sector, so analysis for the gauge sector is exactly the same in the case of the pure ambient theory. So gluons are gapped by fixing, and there are also gapless fermion if you solve the Dirac zero mode equation. And since we finally solving the 2D effective theory, so this gapless fermion can be mapped to the compact boson by this kind of the mapping. And effective theory turns out to be given by compact boson kinetic term plus some coupling between this compact boson and discrete gauge field GL given by this one. And the center vortex can be given by some non-trivial field strength of this discrete gauge field. So although this is a discrete gauge field, but there is a UV cutoff of this effective description, so there can be a non-trivial field strength for this GN gauge field. And the center vortex is characterized by this non-trivial field strength, and you can compute the vertex operator of this center vortex, basically giving the cosine potential for this compact boson. And if you perform dilute gas approximation, instead of having this topological coupling between phi and dA, you now get a cosine type mass term for the compact boson field. And you can compute the partition function like this. And since time is almost out, so if you analyze this kind of the cosine type potential, so details of the analysis depend on whether n is odd or even, but outcome is in both cases you get n minus 2 vacuum and this is consistent with the discrete higher symmetry breaking. And especially important point is we just get n minus 2 vacuum and we do not have extra factor like 2 or something. That suggests that this charge conjugation symmetry is unbroken. Yeah, you can also look at the details of the vacuum expectation value of this compact boson field, and you can indeed check that C symmetry is indeed unbroken. So let me summarize what I have obtained. So we studied QCD with 2-index antisymmetric flux using semiclassical analysis in this femtotorus with non-trivial magnetic flux. And by introducing magnetic flux properly, then so we keep the 4D anomaly in this 2D effective theory, and this suggests that so these two dynamics are constrained by the same anomaly relation. So we can expect that so adiabatic continuity may hold between these two theories. And by solving the theory explicitly, we find n minus 2 vacuum which come out of this spontaneous breaking of the axial symmetry. And the outcome is chiral is broken, but the charge conjugation or fermion parities are unbroken, which suggests that so since unbroken C or fermion parity are key feature for the validity of the large N orient fold equivalent, so our analysis seems to give a positive support for this orient fold equivalence. That's everything. Thank you. Thanks very much for your attention. Yeah.
What can you implement the generate
Yeah.
Yeah, so for that purpose, so we have to analyze this part, but so since topological charge is just 1 over n, so you get 1 over n factor here. And since, so because of overall topological charge has to be integer, so in addition, so we get a cosine type potential, but this is, but regarding the phi periodicity has to be 2 pi originally, so this form is incompatible with the gauge redundancy of the phi. But you get also the L label for the for constraining the fact that so you should get a total topological charge has to be integer. So partition function should be given by summation over L from 0 to n minus 1 with this action, and this phi path integral is periodic in 2 pi. And so that means that so periodic so identification of phi and L should be given by this form. So L is n, L's periodicity is given by n, but phi's periodicity is not a naive one. So if you shift phi by 2 pi, then L should be shifted by this kind of a mark. And if you take into account this definition of the periodicity, then you can find there are n minus 2 values.
Right, but your symmetries of this 2D system are just on Z2, Zn, no?
No. So symmetry is really just the same. So if you so especially when n is odd, so symmetry of the compact T2 cell 2D cell is this U1 and this axial symmetry. So it's the same symmetry
But
property.
one from symmetry is Z2, no?
One form symmetry is Z2 when n is equal.
So all you have is some kind of Z2 with an anomaly. How can you get n?
But I'm using this U1 too.
No, it's not the anomaly between the one form. It's the anomaly between the U1 and the Z2n minus 2 chiral.
Yeah, so I'm using full, not only just one form symmetry, I'm using
Mixed
full.
anomaly between variant number and axis.
Exactly.
Variant number and axis. That's right. It's a four-dimensional version.
Yeah, right. So exactly. So even if we just pay attention to this one form symmetry, so even in 4D, so you cannot prove n minus 2 degeneracy of the vacuum by anomaly matching condition. So you really have to use this U1 part too.
So what do you have B? What is B? B is Z2.
B is so if you introduce
Okay, I got it.
Yeah, fractional
you can
piece
take
of
it to
U1.
Gn2 form.
Okay, so one from symmetry plays no role in this.
Yeah, right. So this quotient, so combined with this quotient, full Gn one whole, in some sense, full Gn one whole symmetry plays an important role.
I mean, there's also a mixed anomaly presumably between the one form symmetry and the axial, right?
Yes, but this actually gives trivial.
Yeah,
It doesn't give us trivial. Yeah, it's
It's
trivial.
not. So there's no.
There is no anomaly. There is no anomaly between the Z2 and the axial.
is it always true? Depending.
And I'm talking about the mixed anomaly between Z2 one form and the Z2n minus 2.
Yeah, maybe. Yeah, I don't remember exactly, but yeah, you studied it very well, right? Yeah.
No other questions? Okay, let's thank you again.
Yeah, thank you so much.